In this video, we are going to do an application of the antiderivative to marginal profit. So this is one of the key topics in Math 30 in the previous calculus course here at SCU. Okay, so I want to look at an example. So the marginal profit to the campus bookstore for X blue books is P prime of X equals 16 minus 0.004X dollars per book. Okay, if the maximum profit is $1,000, find the fixed costs. So to review, remember that the marginal profit function, so it's sort of implied that it's talking about the marginal profit function. The marginal profit function is the derivative of profit. In this case, the problem tells me the derivative of the profit. Okay, so it's talking about the marginal profit function to the campus bookstore when they sell X blue books, and it tells us a formula for that. Okay, and then it also tells us some info about what the max profit is, and it wants us to find the fixed costs. Okay, so just to get us started, let's remember what the formula is for profit. Profit is revenue minus cost. Or if I write this in terms of function notation, I could write P of X for profit equals R of X for revenue, and then minus C of X for cost. So the question ultimately wants me to find the fixed costs. The fixed costs are what my cost function is when I sell no items. So it's C of 0. If we were to sell 0 items, what are sort of the starting costs that we would have? Those are the fixed costs. Okay, so because I'm going to need to figure out what C of 0 is, it means in this equation, P of X equals R of X minus C of X, I'm probably going to have to plug in 0 into that at some point. So we will likely will use the fact that if I plug in 0, we get P of 0 equals R of 0 minus C of 0. And one of the nice things about this equation is we know what R of 0 is. Pause the video for 30 seconds and see if you can figure out what R of 0 is. This is just something that we can use logic on. This is asking, what's the revenue when you sell 0 blue books? So pause it in 4, 3, 2, 1. Pause the video. Pause the video for 30 seconds and see if you can determine what is that revenue. Alright, so hopefully you've done that. Hopefully you paused there for about 30 seconds to try to determine what R of 0 is. But R of 0 is just 0. It's 0 since the revenue from selling 0 items, in this case 0 blue books, that's because we're plugging in X equals 0, should be nothing, should be $0. If we sold no items, then we haven't made any revenue. Okay, so R of 0, we can sort of just logic out that way. Okay, so now I know I'm going to need to get P of X somehow. And I know the derivative of P of X, so let's take the antiderivative. So P of X is the integral of 16 minus 0.004x dx. So let's take the antiderivative. I get P of X equals, the antiderivative of 16 is 16x. And if we use the reverse power rule in the next term, we get minus 0.004x squared divided by that new power, divided by 2. And then I have to put a plus c. And simplifying this, we get P of X equals 16x minus, we'll get 0.002 after I divide that decimal by 2, x squared plus c. All right, so I have the general form of my profit function. So Next, I can use the fact that the problem tells me the max profit. It tells me the max profit is $1,000. So just like in the previous video, when we did an example involving the minimum value, this is talking about the maximum value of the profit. And to figure out where that occurs, we need to first find the critical numbers. Okay, so I'm continuing my work at the top of the page to give myself some more room. But next, we need to find the critical numbers to determine where the profit is maximized. Okay. So at this point, I want you to pause the video one more time. Give yourself about 3 minutes this time and see if you can finish this process of finding the critical numbers and then testing them using our sign chart method that we talked about in the previous video. Okay, 4, 3, 2, 1, pause the video. Pause it for about 3 minutes to try this on your own. Alright, so hopefully you've done that. Hopefully you paused it for about 3 minutes to try that. Okay, so let's talk about it together. Critical numbers would happen either when the derivative equals 0 or the derivative p prime of x is undefined. And just like in the previous example that we did in the last video, our derivative is never undefined here. So this never happens here, because I don't have a situation where plugging in a certain value of x would make a denominator 0, or the inside of a square root negative, or anything like that. Okay, so when is my derivative equal to 0? Well, our derivative was 16 minus 0.004x, and I need to set that equal to 0. If I isolate the 16, we get 16 equals, and then let me convert this decimal to a fraction. So 0.004 as a fraction is 1 over 250, if I work that out. And then I have x. Let's multiply both sides by 250 to get rid of this fraction. So we'll get x equals 16 times 250, or x equals 4,000 if we multiply that out. Okay, so that's my only critical number. That's what made the derivative 0. There's nothing that made the derivative undefined. If there had been something that made the derivative undefined, that also would have been a critical number. Assuming, of course, that it's in the domain of the original function. Okay, but in this case, we don't need to worry about that because our derivative wasn't undefined anywhere. All right, so we are ready for the sign chart. We are ready to make a sign chart now. Okay, so I put 4,000 on it. Put our critical number on it. In this question, though, there's a natural limitation on our variable x. Because x is the number of blue books. It's a quantity. And my quantity can't be smaller than 0. So I'm going to put a bracket here at 0. And the reason, again, is because x is a quantity. So it can't be negative. So that's why I'm putting that bracket there at 0. Okay, so now our sign chart is going to need a row for the derivative and a row for the original function. Okay, so making this table here. And let's pick a test point on either side in each sub-interval. So something between 0 and 400. So maybe 1. That's kind of simple. Something bigger than 4,000. I might pick something like 10,000. It's a very nice number. It's got a bunch of zeros, so it's going to be easy to do computations with. Okay, so if I plug in 1 into the derivative, p prime of 1, we'll get 16 minus 0.004 times 1. And that's going to be a positive number. This is 15.996. So the derivative is positive when I plug in 1. So if the derivative is positive, p of x, the original function, is increasing. So it is going up. All right, so let's plug in our other test point. Let's plug in 10,000. 10,000. Let's put a comma there even. If I plug that in, we get 16 minus 0.004 times 10,000. Okay, so this is 16 minus, multiplying 10,000 times 0.004, we'll get 40. And then 16 minus 40, that is negative 24. All right, so in this other subinterval, our derivative was negative, which means p of x, the original function, is decreasing. And if p of x is decreasing, that means it is going down. Okay, so I have my sign chart done. This is where we need that sentence of justification. To justify, wait, why is this local? At this point, I know it's a local max because my function changes from increasing to decreasing at our critical number. Why is that local max actually the absolute max, the very highest point? So the justification is going to be really similar to the justification in our previous video. We would say that our profit is, let me word it like this. Profit has an absolute max at, what is the value where it occurs? It occurs at x equals 4,000. Since P, profit, is increasing the whole way up until 4,000, so it's increasing for all values of x that are less than 4,000. And P, our profit, is decreasing for all values of x that are greater than 4,000. Okay, and one thing that you might be noticing is, wait, in our number line, it sort of started at 0, but here I said P is increasing for all values of x that are less than 4,000, so everything to the left of 4,000. So technically when I'm saying that P is increasing for all values of x for which our function is defined, things that are in the domain. So it doesn't make sense to talk about our function for negative values of x, for example, because that wouldn't make sense to have negative blue books. Alrighty, so we have the sentence of justification. So let's use now the fact that it tells us the maximum profit. So let's plug in x equals 4,000 into our profit function. Okay, so we know that if we plug in this value, 4,000 blue books, that should give us the maximum possible profit. And in the question, it told us what that maximum profit was. It said the maximum profit was $1,000. Okay, so if I plug in 4,000 into my profit function, this should give me $1,000 for my profit. Okay, so I'll get 16 times 4,000 minus 0.002 times 4,000 squared. So that's plugging 4,000 into my profit function. And then plus c, sorry, I forgot the plus c, equals 1,000. And if I simplify this, we get 32,000 plus c equals 1,000. And then isolating c, we get 1,000 minus 32,000, which is negative 31,000. Okay, so we have our value of c. But remember, what were we going to do to figure out a fixed cost? Well, we were going to plug in 0 into the profit function because p of 0 is equal to r of 0 minus c of 0. And c of 0 was going to be the fixed cost. Okay, so we need to plug 0 into our profit function. Oops, let me just shift it down a little bit. Okay. So note, if I plug 0 into my profit function, that'll just leave me with c, that constant I got. But p of 0 is r of 0 minus c of 0. So one thing to note is this c is this negative 31,000. When I write c of 0 here, this means plug x equals 0 into the cost function. So those two c's are different. Okay, so I want to be clear about that. All right, so, and this equals that constant, which was negative 31,000. All right, and at the start of the video, we said what R of 0 was. The revenue from selling 0 blue books is 0. We wouldn't make anything if we sold 0 blue books. We would make no revenue. And then C of 0, we said was the fixed cost. So negative fixed costs equals negative 31,000. So dividing both sides by that negative 1, we get that the fixed costs are positive 31,000, and the units of costs, units of money in this problem were dollars. So fixed costs are $31,000. And that's my answer. So in terms of our goals for this section, we have finished our last goal, which is we did an application of antiderivatives to marginal profit. So as a preview to the next video, in the next video, we're going to start to look at more challenging antiderivatives. In this section, we just looked at more basic ones. In the next video, we will do antiderivatives like the integral of square root of 1 plus 4x squared, and then with an x on the top, dx. This isn't something that we know how to do just yet. So we need a new technique for this. Need new technique. And we will talk about that in the next section, 6.2.